Okay, that claims to have started a new recording. So, good morning everyone. Welcome to Lecture 7 of Superconductivity. This lecture has a demo which this camera is not going to pick up, but which Andy has kindly brought in. Do you want to say something about what this is so that people can come and look afterwards?
So the people who weren't here before, we have levitation going on at room temperature here. And this is, to me, a very powerful demonstration because this is not because of the spin in graphite, which this is a sheet of. This is a diamagnetic response of graphite. And in the end, when it's not spin involved, you can always write that down in terms of a sum of currents, right? And that is an equilibrium phenomenon because the thing is going to stay there forever. Right, and it was very interesting for me to first see this kind of thing because it got me thinking really hard about, well, what is the essence of a superconductor then, right? And the answer is that these currents are flowing, but if you like, the real currents will be very short length scale things. So Chris will, at some point, has already derived the magnetic penetration depth. What you're essentially saying here is that the same London equations or the same electromagnetic equations apply in this case, but the actual physical radius of the currents is much, much smaller than the penetration depth, which is of the same order in graphite as it is in any of the superconductors Chris has talked about. So this is diamagnetic, but inefficiently diamagnetic. And many, many materials are like that. It's just that their mass density is higher, so the diamagnetic force isn't enough to levitate them. That's the key thing that's here. And the other thing to say is, who's heard of a famous other example of something non-superconducting being levitated? Yes?
This flying, or this levitating frog.
Yeah, the levitating frog. So that was done in a 20-odd Tesla or 30 Tesla field at a high field lab because the diamagnetic force to mass ratio is different, but it can be done in a high field lab. And for those of you who don't know that story, that gained Andre Geim the Ig Nobel Prize several years before he got the real Nobel Prize, and he's the only person to have achieved that combination in that order. Okay.
Excellent. Great, thanks very much for bringing this in. Just as a demo, you can pass. You do it carefully. The standard demo that there are no strings. There you go.
So I remember it, I'll take it away.
Excellent. Yeah, thanks for bringing that in. And yeah, perfectly good points. So, as we were discussing last time with the Meissner effect, really all we put in was the idea that there was a persistent current, and the rest was electromagnetism, so it should work with anything that can run a good enough persistent current. And there's an example. So, yeah, just to remind you where we were with superconductivity, we talked about some of the broad phenomenology, flux expulsion, the anomaly in the specific heat capacity and the low temperature behavior, the fact that the superconducting phase is fully gapped, at least in the simplest cases, unlike the superfluid. And then we talked about how we can write a theory for that, this Landau-Ginzburg free energy, which includes the magnetic field in the form of a vector potential. And we've been carefully trying to write down only gauge invariant combinations. So for example, when we wrote the supercurrent, which is often just written as being proportional to the vector potential, we were careful to write the full expression, which is, with prefactors, the gradient of the phase of the superconducting order parameter plus 2En. That combination is gauge invariant. And basically we substituted that back into the free energy used Maxwell's equations, that allowed us to write a theory for the interior of the superconductor entirely in terms of what the magnetic field was doing. And we showed that that leads to the London equation, which gives you exponential decay of the magnetic field as you move in from the surface. So we can show that the sort of resting state of the superconductor is a zero field state, and if you put something on the boundary that's inconsistent with that, it will decay exponentially over a length scale, which is the London penetration depth. So today I'd like to unpack some consequences of that. And in particular, we're going to start to look at things that require more than just having persistent currents and that actually have to do with quantization. And the fact that there is this macroscopic wave function for the superconductor, and that wave function has to be single valued. So this is basically about vortices and flux quantization. We might get as far as the Josephson effect, but let's see how we go. Josephson was the first Welshman to win a Nobel Prize in physics, so it's another first. So let's consider, and we'll see shortly why we do it, a superconducting sample that has a hole in the middle. So there's this cavity, there's a large bulk superconductor here, and let's take this expression for the current and ask what we can predict from it. So, far from the edges, we expect the supercurrent to be zero. And we saw an example of that in the Meissner calculation last time. So you put a magnetic field on the edge, the sample runs supercurrents, but the supercurrents only go in as far as the field goes in, basically, which is the London penetration depth. So if we're more than a penetration depth from the wall of the cavity and the edge of the superconductor, we expect that the supercurrent in the bulk will be zero. And as you can see from that equation, it follows that h bar grad theta is equal to minus 2EA. Or if we move the h bar across, the gradient of the phase is minus 2E over h bar A. Now, an obvious solution to that is just to set the gradient of the phase and the vector potential to zero. But that's not the only solution. So let me integrate this equation round a loop, which is deep in the superconductor, nowhere near the edges. And then get the integral around this closed contour of grad theta dot dl is minus 2E over h bar, the integral around this contour of the vector potential. The integral of a gradient is an exact, so this is an exact derivative, so this just gives me the change in the phase of the order parameter as I go round the contour, which I'll call delta theta. And by Stokes' theorem, I can transform this into the integral over the flux through a surface S of the curl of A, where the surface S is any surface bounded by this curve. But of course we know that curl of the vector potential is just the magnetic field. And so the flux of the magnetic field through the surface is the magnetic flux. And so this is minus 2E over h bar times the flux threading the loop. Now, if we didn't have the cavity, the flux threading the loop would be 0, because there would be no magnetic field anywhere inside. But of course the cavity is normal and might be carrying a magnetic field. So we shouldn't assume that this flux is necessarily 0, because there could be some flux in the cavity, maybe some phi external, that we applied. And so you say, well, maybe this is fine, right? We just put the external flux here, and that will tell us the phase change as we go round the loop. But there's a problem, because suppose that phase change was 2 pi, and then I slightly increase the flux in the cavity. The phase change would then be 2 pi plus epsilon, but that means that the superconducting order parameter isn't single valued. And so it can't be the case that small changes in this flux produce small changes in delta theta, because delta theta has to be 2 pi times an integer for the order parameter to be single valued. We built the whole theory on the idea that the order parameter is single valued. Otherwise, what do I mean when I say theta at r? So what that tells me is that this flux over here is quantized. Now that doesn't mean that the flux that I applied using my coils is quantized. It means that if I put a non-integer amount of flux through here, the superconductor will adjust by running supercurrents around the boundary of the cavity, and it will go to the closest total flux, which is consistent with the single valuedness of the order parameter. So phi, which is the total flux through the loop, which is phi external plus phi induced, is equal to, okay, we don't need the minus sign because we could have taken the integer to be negative. So we get, so the blah, blah, blah. So that's pi h bar over E, which is h, the regular Planck constant, over 2e times an integer. So this gives a superconducting flux quantum, often written as phi naught, which is Planck's constant divided by twice the positron charge. It's twice because that's the thing that we put into the Ginzburg-Landau theory. Because of the experimental observation that it was a better fit to the data, we all sort of know that it's coming about because these bosons are pairs of electrons. So it's important to note that that's not the same as the flux quantum that you see in, for example, the quantum Hall effect. There you're looking at the response of single electrons to an applied field, and the flux quantum there is h over E. Here we're looking at the response of doubly charged bosons to the field, and so the flux quantum is h over 2e. And so flux quantization is the statement that the total flux wrapped by the loop must be an integer multiple of this superconducting flux quantum. You simply can't write an equilibrium state where it isn't. Which must mean that if you start off with the superconductor with 0 flux in the cavity and then you impose some by running a current through some coils, it will adjust to run some supercurrents round the edge of the cavity, and it will adjust in whatever way is necessary to kind of swim to the nearest value of the flux quantum. That has an interesting feature, of course, which is that if I put a number of flux quanta through this cavity, which is an integer plus a half, then I have two degenerate equilibrium states for the superconductor. It could run a current one way and round the flux up, or it could run a current the other and round the flux down. And those are genuinely degenerate states, and you can, if the superconductor is small enough, kick it between those two states, and there are qubit designs that are sort of basically based on that fact. So you can use those two circulating states of the supercurrent, one anti-clockwise and one clockwise, as states of a qubit. Good. So that's actually quite a simple observation, but it has weird consequences. So I thought we'd start there, and then think about how these cavities might come about.
Could I just say, I think it's been reflected also in some of the questioning last time, that, you know, what this is doing, and what superconductors do, like in many cases, is they face most of us to look at the bits of quantum mechanics that we glossed over and never quite understood, right? I mean, it puts this canonical momentum issue just up front and center. You see it in other places, but you simply cannot avoid its physical reality when you look at superconductors.
Absolutely. And notice that it emphasizes that there is a reality to the superconducting order parameter. So although there's only one gauge invariant combination, which is this combination here, so gradients of the order parameter by themselves are not gauge invariant. The order parameter is real enough that demanding that it be single valued gets you observable consequences. And when we get to the Josephson effect, we'll see another case where it's very hard to explain what's going on if you don't talk about the order parameter.
So all of this went on in atoms, but in magnetic fields, but we kind of didn't pay attention in that bit of our atomic physics course. Right?
I mean, in some sense, the single valuedness argument is there from the very beginning in atoms, right? As quantization comes from a single valuedness requirement.
So I had a couple questions. The first one is, if you were to start with, like, say, one flux of, one flux through that cavity, and you were to slightly increase it, you would get a superconducting current, but would it just turn off once you get to two flux?
Yeah, it would flip at 1.5 fluxes. Right? So what you have. So let's plot as a function of externally applied flux in the cavity the total flux inside the blue loop, or threading the blue loop. So the naive expectation would be this, but that's not consistent with flux quantization. So what it will actually do is, so let me mark the flux quanta along here. So each of these ticks is a flux quantum. So up to half a flux quantum of applied field, it will screen it out. Then when we get to half a flux quantum, it will jump to rounding it up to a full flux quantum. And then it will sit there until you get to 1.5 flux quanta of applied field, and then it will jump to rounding it up to 2 flux quanta, and so on. GCSE technical drawing in full effect. So it will look like this in an ideal case. I mean, obviously, in reality, you'll be doing this as a function of time. It will take some time to adjust. However you really do this experiment, there'll be some rounding of these steps. But if you just ask, what's the equilibrium configuration, this is what it is. So what current am I running to generate this? So the sort of magnitude of the supercurrent that's running round the loop. So initially I'm running a screening current, which I will call negative. And then just at this point, it's going to have to reverse the direction of that supercurrent because now it wants to increase the field in the cavity relative to the applied one. So that will jump up to some value here. The vertical scale is arbitrary. And then coast back down to 0 because at this point, the external field already obeys flux quantization and it doesn't need any more current. And so it'll just keep doing this sawtooth. And every time we have one of these steps in flux, we'll get a jump in the current. And again, the perfect sharpness of this is a theorist's idealization. So that's what's going on.
And the second question was, this does look very similar to Lenz's law that we see in a classical metal, where you get creation of current to oppose a changing flux. So is this like, is there any sort of effect that well, I mean, obviously if you have a changing flux, you're going to get a changing supercurrent. So is that just follow from, like, does Lenz's law predict that, or is there a deviation from that here?
So Lenz's law tells you that changes in flux will create an EMF. To say that that EMF creates a current also requires you to have some constitutive equation. So normally we assume that the thing we're dealing with is an ohmic conductor, so that if I generate an EMF, that EMF will run a current that's proportional to the EMF. So normally that's what you do. You change the flux through a metal loop. That generates an EMF round the loop by, well, Faraday's law. So Lenz's law is the sign, but Faraday's law is the thing. And that will run a current which will oppose it and try to steady the field. But the crucial difference is that is only sensitive to field changes. So I can have a static configuration with a regular metal where there is a field through the loop, but because it's not changing, no currents are driven. Here I have a static configuration for most of these values where there is a field through the loop and it's running a persistent current. And it always, the field is always screened down to 0 inside the superconductor. So it's different by a power of a time derivative, basically, as lots of the physics of superconductors is. Right? So we didn't talk about London's first law, but London's first law actually says this. And that's, again, different from Ohm's law by a time derivative. So lots of the kind of dynamics of superconductors is just kind of slipped by a time derivative from the dynamics of regular ohmic conductors. But I'm deliberately not trying to talk about dynamics here. We can just ask what are the available static configurations. And of course we know that static configurations in superconductors can include supercurrents. And what we find is that most of the static configurations you can generate by putting a magnetic field through a superconducting cavity will induce supercurrents. Andy?
Fine, yeah, that's true. That must be somehow telling us that Lenz's law is a classical law in some ways, though, because take an Aronoff-Bohm ring, as you talked about before, right? There, what you've done is to take a metal down to the length scales where you could think of a coherent, wave function around it, right? And you're going to get a lot of the same effects going on in terms of the flux that's allowed through the ring. It's going to be as h over e, not as h over 2e.
I don't think that's right for a Aronoff-Bohm. So what you do with a Aronoff-Bohm is you take a ring configuration and you thread a flux through it. And what you see is that if you measure the resistance between these two terminals, that goes like something which is periodic. Let's be careful, because this is not the superconducting flux quantum, just the regular one. But this isn't a quantization condition. This is, you can have any flux you like through the center of that ring. It's just that the properties that you observe in electrical transport around the ring depend on that flux in a periodic way. That's different from actually interfering with the flux itself. So here, in this experiment, the motion of the charges has negligible electromagnetic feedback. This is just like an externally applied flux that determines what resistivity you'll see. So in this experiment, the flux acts on the electrons, but not really vice versa. In this experiment, the back action's really important.
Very good, yeah.
So, yeah.
But you don't need to study Aronoff-Bohm anymore using resistance, right? There are these famous experiments with squid microscope.
Yeah, absolutely.
Essentially observing the,
Yeah, so that certainly demonstrates the wave nature of the electrons, and it demonstrates this strange feature that no electron in this experiment is actually passing through the magnetic field, and yet by passing on either side of it, they notice that it's there. That feels odd, right? If you think locality is important to you, but we sort of know that there are non-local aspects to quantum mechanics. So here's another one. But in terms of, this is very much a one-way thing. The field is just what it is. It acts on the electrons, and then properties of the electrons are altered. In the superconductor, the supercurrents act back and alter the field in the cavity. Or at least alter the total flux through the loop. They generate something which is comparable to the field in the cavity.
but in an atom, you're going to say that in an atom, it will be like the Aronoff-Bohm ring, in an atom in a magnetic field.
It is.
Very good. And so can we identify physically what the difference, say, between the atom, because you've got the single valued argument in an atom.
Yeah.
What is it, you've talked about, this might be a really good way of visualizing what you were saying about you can only think of one field in a superconductor.
I mean, the difference is basically condensation. So the reason that the superconductor is able to act back on the field and is strong enough to have perfect diamagnetism is that these effects that look like single particle quantum effects are magnified by the total number of particles present, which are behaving coherently. So the square modulus of the ground state superconducting order parameter, which the integral over the sample of the ground state superconducting order parameter, this will be 1 for a quantum particle. It's the total number of charged bosons for the case of the superconductor.
Seems like a magnitude rather than a magnitude thing rather than a thing of principle. Can I not imagine creating a one electron system with the right length scales and flux scales or something to mirror that?
You probably can, but that n is very big.
I know.
Yeah. I mean, it is ultimately...
N is very big, but an atom's very small. Okay.
But yeah, I mean, I think...
Don't let me disrupt the...
I think it is ultimately a matter of degree. I mean, a lot of what we're seeing here is really single particle quantum mechanics. But because it's amplified by this condensation, we have to think about things like the back action of the supercurrents on the field in a way that we wouldn't if they were carried by a small number of particles.
How does the supercurrent knows what is the nearest flux quantum? Like, it's like it doesn't know mathematics, so statistics.
Yeah, I mean, you'd be surprised what nature knows. Yeah, I mean, the dynamics of this, I guess, are probably complicated. Right? So what you will actually do is start off in some equilibrium state, and then you'll perturb it by putting some, by changing the magnetic field through the cavity. That change in the magnetic field through the cavity will generate electromotive forces, and you'll have some period where everything depends on time. So we're not trying to describe that, and quite deliberately, because I guess it's difficult. I mean, I don't really know how to describe it. We're just saying, we can see what the end states have to be, because these are the only available time-independent states. So unless it's going to oscillate forever, which feels like it shouldn't be allowed for perpetual motion machine reasons, it's got to settle to one of these states.
It's interesting to think it's like it is choosing a nearest minima of some thermodynamic potential, let's say, right?
Yeah. Yeah, and I mean that usually works because you can think of it, if it's slow enough, as basically going downhill in some free energy landscape. And we can do that here. So people draw energy landscapes for these things as a function of the flux in the cavity. And so there you really do see that it's a multi-minimum structure and there's just sort of a downhill force. But that's already subject to some quasi-adiabatic assumption, which might not be right? But the argument is whatever you do, basically, it's got to reach one of these because there's nowhere else it can go. Other questions? Okay, let me knit together now this observation about cavities and fluxes with the discussion we were having last week about superconductors going normal if you put a large enough field on them. So in the simplest case, we considered last time just two extreme cases, right? You have a superconductor in a cavity that imposes a field, and we looked at the energy where the superconductor is put in the normal state and the field is allowed to go right through, and we looked at the energy where the superconductor is in the superconducting state and the field has to go round. And we saw that in the first case, you miss out on the condensation energy of the superconductor, but you save energy in the magnetic field because you don't have to compress the field lines to move them round the superconductor. Whereas in the Meissner case, you lower your energy by the condensation energy, but you raise it by the energy cost of wrapping the field lines round the sample. And so if you make the field large enough, that field line energy cost will win and the superconductor will go normal. But this raises an interesting possibility. Obviously, if you had a superconductor with cavities, then you could thread the magnetic field through the cavities. And this might remind you of our discussion of how superfluids accommodate rotation. Right? Superflow is irrotational, but if I make some normal vortex cores, I can carry the rotation in there. And that turns out to be a better solution than ignoring the rotation of the surroundings. In just the same way, it is sometimes preferable to introduce vortices into the superconductor as a way of allowing the field through, rather than letting the entire superconductor go normal. But there's an interesting difference from the superfluid case. In the superfluid case, you always wanted to introduce vortices. And that's because what you gain in terms of rotation decays like a power law, whereas what you lose in terms of condensation energy decays exponentially. So the energy loss involved in creating a vortex in terms of losing your superfluidity is always outweighed by the energy gain from allowing some rotation into the sample. But superconductors are different because, as we've discussed, they have these two length scales. So if I were to make a vortex at the origin, we know that the superconducting order parameter will be 0 at the center of the vortex And we calculated, just the same calculation as the superfluid, that it will recover over a length scale set by the coherence length. And we've also calculated, just copying our result from the boundary Meissner effect, that an applied field will decay exponentially as we go into the bulk of the superconductor, and it will decay on a length scale given by the London penetration depth. Now, obviously, details of the calculation aren't the same, right? We did the Meissner calculation assuming that the superconducting order parameter was strictly constant. Clearly here, the superconducting order parameter is not strictly constant, but it's the same length scales that turn up if you do these corrections, just with slightly different factors in front of them. And this makes a difference because if the London penetration depth is much greater than the coherence length, it is well worth introducing a vortex, because the change in energy of the system is proportional to something that goes like the square of the coherence length and is positive, right? This is the cost of drilling that hole in your superconductor, right? So you've lost some condensation energy, but minus some other number times the magnetic field that you've allowed to be introduced. Oh, sorry. That's got the field in, times the square of the London penetration depth. So you can work out the energy increase because you've spoiled the uniform superconducting state versus the energy decrease because you now don't have to compress the field lines so much because you can thread them through the vortex core. And in the case where the London penetration depth is much bigger than the coherence length, the volume in which you can admit the field is much bigger than the volume in which you had to lose the superconductivity, so that's worth doing. This energy change will be negative, and so you will introduce a vortex. Conversely, obviously, if the London penetration depth is much less than the coherence length, the vortex is not worth it. Energetically, you're better to just hang on until the magnetic pressure becomes too great and then just go normal all at once. So there are these two types of behavior which depend on the ratio between the penetration depth and the coherence length in the superconductor. And you might wonder, is there some relation that these have to have to each other? And the answer, it turns out, is no. Right? So there are superconductors of both of these types. Unfortunately, I've written them the wrong way round. This kind of superconductor, where it is never worth admitting a vortex, i.e. where the London penetration depth is short compared to the coherence length, is called type 1. And this type of superconductor, where it is worth admitting a vortex, is called type 2. And the actual difference in ratios is given by the turns out there's a root 2 as these things are conventionally defined. So if the London penetration depth is less than the coherence length over root 2, your superconductor is type 1. If the London penetration depth is greater than the coherence length over root 2, your superconductor is type 2. And these respond quite differently to the application of magnetic fields. The type 2 superconductor at quite low fields will start admitting vortices. The number of vortices will increase as the field is increased. Eventually, as in the superfluid, the vortices will overlap and the whole sample will go normal. Whereas in a type 1 superconductor, you just get a perfect Meissner effect until you hit a critical magnetic field, and then it just drops out of the superconducting phase into the normal one.
Can you explain again why we have a gain of lambda L squared? Because I have a feeling that if lambda L is small, we will need a strong field, and therefore
Yeah, so this is why last week I went through that calculation about how much energy it costs to expel the field. Right? So what we showed in lecture 5 or 6, I can't remember which, was that if I take a box with a constant magnetic field B inside it, and then I introduce a region in that box and force the field to go round it, then the energy change going from here to here is plus the volume of this bit that I've excluded times the square of the field over 2 mu naught. Which feels odd, right? It feels like you should have to do some kind of complicated calculation to work out the energy change in the field lines. But as we showed, in the case where this volume is small compared to the overall box, actually the energy cost of expelling the field from this volume is just proportional to the volume itself. So if expelling the field from a volume makes the energy go up, readmitting the field into a volume makes the energy go down.
yes, yeah, but here we are expelling, and the fact that the field was increasing was spread out in all the big box, and so it spread on the total minus V. Whereas here we take B inside our superconductor, and therefore it's spread in a much smaller region.
Yeah, that's right, but the correct comparison is still between the volume of the vortex core and the volume of the whole box. It's just, right? It's just like this,
Okay.
except now the small region is the core of our vortex.
Okay. Yeah. Okay, I see. Yeah.
So we've expelled field from the bulk superconductor. That's already cost us B squared times the superconductor times the sample volume. And now we're saying, well, maybe if I create a vortex, I can get some of that back, lower the energy by B squared times the vortex volume.
Yeah. Okay, yeah.
So in principle, obviously that's always good, but it costs you some condensation energy. And so if I assume that, I'm assuming here the vortex is just a cylinder going through the sample, so then the volume of the region where I have to kill the order parameter is the height times square of the coherence length. The volume of the region where I can admit the field is the height times the square of the London penetration depth.
Okay, yeah. And so therefore here we will have vortices inside all V, in the sense that V will be vanishing nowhere because to have greater repetition. Yeah.
Yeah, that's right. So in the strongly type 2 case, if I have a set of vortices like this, the superconducting order parameter looks like this. So from that point of view, most of the sample is superconducting.
Yeah.
But the magnetic field profile looks like this. So a strongly type 2 superconductor can admit magnetic field into its entire bulk without losing at least the condensation. Now, you still have to ask, well, is this still a superconductor in the sense that it has zero resistivity? And the answer is no, because the motion of the vortices generates dissipation. So in the perfectly clean case, actually, the vortex phase is in a sense not superconducting if you talk about transport, but it is in some sense superconducting in that it has a robust superconducting order parameter in most of its bulk. If you used an STM, you could see the superconducting gap and so on. So yeah, that's called flux flow resistivity. But then there are additional complications, like real superconductors are dirty, and so the vortices tend to pin. So actually what you find is that you first have a Meissner phase, then you admit some vortices, but they stick to impurities in the sample, and so they don't flow. And so that sample still superconducts in an electrical transport sense. And then at some vortex density, they depin, then they start flowing. You've still got superconductivity in the sense that you have the order parameter non-zero, but now you don't have a resistive signature of superconductivity because you've got resistance coming from the flow of the vortices through the sample. So it actually gets quite complicated once you ask what real superconductors do, but a lot of the understanding of what real superconductors do is based on this idealized picture that for a type 2 superconductor, at relatively modest fields, even while it remains superconducting, it will start admitting these vortices. Loads of questions. Paul?
So if you, this was only if you apply an external field, right? And if you think naively about applying a electric current through the system, then I mean, of course, from the superconductor point of view, it's like ground state current, so there's not necessarily a magnetic field induced. But if you just think about electromagnetism, then there's there are sort of electrons flowing, so there should be a magnetic field. Is there like some back action through this, where basically a current will induce some of these fluxes? So some of these vortices to pop up.
Do you generate enough magnetic field from the supercurrents
Exactly.
to start putting vortices through the sample? So I don't recall discussion of such a case.
It is discussed in material science, and I think the answer is yes. Well, okay, the self field can be important in driving you normal, whether you go normal, because it's current going that way down a wire, you've got self fields like this, and it's going to be a little bit more like mixed state type answers in a type 1 or something like that. But I mean, the scales do matter. I believe engineers believe that the self field does matter, and because there's a phenomenon called the critical current, and the critical current, when you have pinned vortices, the current itself as well, the current itself leads to there being forces on the vortices. Right, so there will be then some maximum current at which they depin and begin to flow, then you go normal. But I think there's a second kind of critical current which is to do with the generation of the self field.
Excellent. Yeah, so it sounds like the answer is yes. But yeah, I don't know much about these practicalities. Not that I'm saying that I shouldn't, but I just don't. Yeah.
Okay. So I have a question. So about the square two relationship between the lambda, the penetration depth, and the healing length to decide the type 1, type 2. Is that a exactly number, or is it just a roughly number?
It's exact it's exact within Ginzburg-Landau theory and with the standard definitions of the London penetration depth and the coherence length.
Okay.
And it comes basically from the solution for what the order parameter does inside the vortex core.
And also, so in some cases, for example, in some thin film, that all the superconductors become type 2 superconductor. And why, do you have any idea why the thin film always is type 2 superconductors?
I think that you may have to be very careful there between the vortex state and the mixed state, right? So the mixed state would say that when you put in too extreme a situation, like say a thin film, and you're forcing the field line to really do crazy things, there's another lowest energy solution which can be stripes, if you like, at times, or macroscopic bits of superconductor and normal, and superconductor and normal. And that's not to do with, there's no flux quantized threading there, I don't think, right? But it is an inhomogeneous material which has superconducting and normal parts. And that's called the mixed state as opposed to the vortex state. And some of what you say, I think it would be mixed state, not vortex state.
Okay, so,
Great, thank you. Parasol.
Is there a way of predicting which metallic state the vortex would go towards? Like, is it always going to be a Fermi liquid, or could it be something else?
That's a very good question, and there's been a lot of work in the cuprates on what actually happens in the vortex cores. All one can say in general is it will be the lowest free energy normal state under the field conditions that apply in the vortex core. And most of the time, if your superconductor formed out of a fairly robust Fermi liquid, then the nearest state in free energy is just going to be that Fermi liquid in a field. So in conventional cases where there's like a phonon-driven superconducting instability on the background of an otherwise perfectly good metal, the expectation would be that the vortex core would be described by Fermi liquid theory insofar as it's large enough for Fermi liquid theory to make sense. Obviously, if the coherence length gets very short and comparable to the lattice spacing, then you can't really use continuum theories at all to describe what's going on in there. There are certain superconductors where you get bound states formed inside the vortices. There's lots of very interesting physics there, and sometimes lattice details matter. But if you're in a material where you already had significant phase competition before you into superconductor, then what it chooses to do in the center of the vortex may be quite a delicate question and may depend on free energy effects from how well your normal state interfaces with the edge of the vortex, not just the sort of bulk free energy.
And you certainly do sometimes pick up non-standard. There's a spin density wave and probably a charge density wave as well to be found in cuprate vortex cores, right? Whereas, of course, then you have a metal as well, right? With the residual bits of Fermi surface, and then the assumption at the moment is that that's still a Fermi liquid. So you can pick up, what you say about the free energy is exactly right. You can pick up really quite complicated phase competition in vortex cores, I think.
Yeah. In principle, any phase that it can find that will admit a magnetic field, which is in practice basically any non-superconducting phase, would do. And it will therefore go for the one that has the lowest free energy, but potentially including boundary effects.
But the trouble is also what Chris was saying, the most exotic superconductors where we might wonder about them condensing from non-Fermi liquid phases have very short coherence lengths. So this issue of not being able to use a continuum theory in the vortex core always comes up.
In an ideal world, of course, the coherence length would be much greater than the lattice spacing, and the London penetration depth will be much greater than that. But nature doesn't always give you as many orders of magnitude as you'd like to play with there. Good. Other questions? Okay, so let's just draw the two basic phase diagrams that come out of that consideration. So now we're going to think of a case where we subject a superconducting sample to a magnetic field and put it at a certain temperature, and we're going to ask what do we expect to see depending on whether it's type 1 or type 2. And this is really just to give you a sense of how the temperature and field effects into play. So if I have a type 1 superconductor, which is the one without vortices, then if B is my applied field, which some people call H, and T is my temperature, there is some critical field where even at 0 temperature, the superconductor would go normal, because it can no longer expel the field except by paying more than the condensation energy. And that comes down and hits 0 at Tc. So there is a critical field as a function of temperature, which is the field at which the superconductor at that temperature will go normal. And there are just two phases. There's the Meissner phase and the normal phase. So the Meissner phase has perfect diamagnetism. It completely excludes the applied field. And then just when you reach this line, the superconductivity just dies in the entire sample and it goes normal. This might raise a worry for you, because reminding you of thermal effects will remind you that the coherence length is temperature dependent, because it depends on that A parameter in the Ginzburg-Landau theory. So we've already argued that at least near the transition, the coherence length diverges like 1 over the square root of the thermal distance from the transition. So what does that do to our classification of type 1 and type 2? Whether it was worth introducing a vortex depended on the ratio between the London penetration depth and the coherence length. If the coherence length is changing with temperature, then you might think that the superconductor could be type 1 at low temperatures and type 2 at high temperatures. There's a remarkable fact, at least within the Ginzburg-Landau theory, which is that even though these are different functions of the parameters of the problem, they diverge as you approach Tc in the same way. So at least within the Ginzburg-Landau theory, that ratio is independent of temperature. Now in real samples, it's not exactly independent of temperature, but that basic temperature independence of the ratio means that the ratio doesn't vary all that much with temperature in typical samples. And so in most cases, you can just say this material is always type 1 or this material is always type 2. But it's worth thinking about that. So when I was writing the energetic conditions, obviously I was working at 0 temperature. It wouldn't have been crazy to think that maybe that calculation changed significantly as the temperature was raised. In Ginzburg-Landau theory, it doesn't. So the vortex cores get bigger as you heat the superconductor, but the field also penetrates better. And so if it was worth making a vortex at low temperatures, it's worth making one at high temperatures too.
But again, this calls into question a lot of our fundamental assumptions with Ginzburg-Landau theory,
Right.
which is supposed only to hold near Tc, and yet we use it to derive or to justify these phase diagrams.
Absolutely.
You know, that's just like the rest of us, you just go, okay, it's the way it is.
We can do a little bit better than that. Because we can ask, so what you would think is that as I cool down, I'm going to need more of the terms in the Ginzburg-Landau expansion. If I write a theory with those higher terms and then renormalize it, so kind of zoom out to longer length scales, the higher terms get smaller again. So there is actually a better justification than just saying we have to be near Tc. It's that if I write a theory with the higher terms that I dropped, and then renormalize it so that it describes just long wavelength phenomena, those higher terms get smaller anyway in the long wavelength effective theory, and in the limit where you're describing very long wavelengths, they go to 0. Now that doesn't completely save you, because of course when we talk about vortices, we're not talking about infinitely long wavelengths. So it's actually built on the idea that by the time you've renormalized out to the vortex size, vortices, those higher terms have already become unimportant. And that could not be right in some cases. But then those are probably the cases where lattice effects in describing the vortex core were important anyway. So I think the picture would be that the renormalization group theory tells you that insofar as you have a continuum theory at all, you're safe in dropping those higher terms. But of course, some physical superconductors won't be described perfectly by any continuum theory. And then we really don't know what to do. Okay, so then type 2, which we've already sort of verbally alluded to, but it's worth drawing it, if only for the tape. Looks like this, so there's still a thermodynamic critical temperature. But now what you will have is some lower temperature line, which we might call, because people do call it that, BC1 of temperature, and an upper critical line, BC2 of temperature. And so now we have three phases. We have the normal state, we have the vortex state, and we have the Meissner state. And this statement about the London penetration depth and the coherence length scaling together basically tells you that if we have a vortex phase and a Meissner phase at low temperatures, we will also have a vortex phase and a Meissner phase at any temperature, right up to Tc. So even very near Tc, there's a region where the perfect Meissner effect is maintained, a region where you admit vortices, and then a normal phase. And as we've discussed, disorder effects can be important in the vortex phase. So actually in this ideal phase diagram, only the Meissner phase would show a transport signature of superconductivity. There would be resistance because of vortex motion in the vortex phase. But if you have some disorder, the vortices will pin, then you may find that this vortex phase splits into a sort of vortex solid and a vortex liquid, and there's all sorts of interesting stuff there.
Probably worth mentioning that BC in type 1 superconductor, I believe, as far as we know, is always first order, right? Mm-hmm. First order phase transition. Whereas BC2 is supposed to be a second order phase transition, but only under a lot of assumptions, right? So in real superconductors, BC2 is not a well-defined line that you find easily with a phase transition.
Mm-hmm. Okay.
So it's a crossover just for people who are going to go on and study anything, say a high TC superconductor. There's arguments for years and years and years about, you always use some arbitrary criterion to define BC2. Mm-hmm. And there's nothing to prevent you having vortex-like excitations into the so-called normal state. Mm-hmm. And there's the thought that they may even go on for tens of Kelvin above the apparent TC.
Mm-hmm. Yeah, I mean, I guess it's worth saying in general that there are fluctuation effects around critical temperatures and critical fields in superconductors, or at least there can be. And that in lower dimensions, those fluctuation effects become more extreme. So there's this work from the 1970s by Markey and Thompson and Aslamasov and Larkin and others, where they ask, if obviously on average, right, and the Ginzburg-Landau theory is an average theory, the average order parameter is 0 above Tc and it's non-zero below Tc, but there will be spatial fluctuations. And if a very small order parameter is spatially fluctuating, then surely it will hit 0 at some point. Right? So once you allow spatial fluctuations, you realize there's a zone around Tc where actually, in a snapshot of the sample, parts of it will be superconducting, parts of it will be normal, and all of that's fluctuating around. and the effect of those fluctuations feeds back on TC and usually pushes it down. Right? So fluctuations mean that you don't develop superconductivity at the temperature where your mean field theory would have told you you should, because you don't really develop superconductivity until the order parameter has lifted off from 0 everywhere, including these fluctuations. So yeah, there's lots of theory around that, and you should always be aware that these diagrams are mean field diagrams that are ignoring a lot of information about spatial fluctuations. We've only put spatial variation in here because it's such a huge phase that we were forced to. I mean, if we really stuck to the principles of mean field theory, we could never describe the vortex phase. We've already deviated from it and said, well, we're going to consider some sort of phase separation, but in a static and well-controlled way. And just to say a little more about the vortex matter that results, so you remember that for superfluids, we had a bit of a discussion about, as I rotate the bucket faster, does it want to beef up the circulation of the vortex in the middle of the bucket, or does it want to introduce extra vortices? You could ask exactly the same question here, right? We've argued that in a type 2 superconductor, it's worth introducing a single vortex. We know that that vortex will carry an integer number of flux quanta. But there's a question of, once my external field gets to a level where I would like to have 2 vortices, should I have 2 single quantum vortices, or should I have 1 double vortex? And so there is that question, 2 n equals 1 vortices, or 1 n equals 2 vortex. And there are various ways to argue that it's actually this answer, as it was in the superfluid, but basically the point is that all of the energies go like the square of stuff. So if I look at the supercurrent energy cost, which looks like some integral over space of the square of the supercurrent density. If I do 2 vortices, so say this is the energy I had for a single vortex. If I do 2 vortices, that doubles. But if I have an n equals 2 vortex, then I need twice the supercurrent, which means the energy quadruples. So the fact that these energies depend on squares of currents basically always tells you that you're better off having a large number of small vortices than a small number of large ones. Yeah.
Just to get back at the phase diagram, in which phases will we see the superconductor levitating on magnet, just to have an image picture?
So you will see levitation in both of these. Okay. But actually exactly what you see in the vortex phase is complicated and is also disorder dependent. So if you actually take one of these kits where you levitate a superconductor over a magnet, you may have noticed that you have to kind of press the superconductor down onto the magnet to get it to stick. Yeah. What are you doing there? You're creating vortices in the sample which then pin. And you can tell that they're pinned because if you rotate the superconducting sample, there's a restoring force. Now, if you had perfectly mobile vortices, That wouldn't happen. I could punch my flux lines through the superconductor, make vortices, then I could just turn the superconductor and the vortices could stick to the field lines and the rest of the material could turn. So that restoring force is evidence that not only have you admitted vortices to the superconductor, but you've pinned them. And that rotational restoring force is the field lines being sort of twisted in the gap between the superconductor and the magnet, and then they twist back.
So it's almost always a vortex phase.
Yeah. And the other, even more spectacular point of those demonstrations is that you've got the superconductor levitating over the magnet, turn it upside down and it's still there.
Yeah.
Right? Because, there's too much energy to try and move the vortices that you created. Mm-hmm. So if you tried to do it in the Meissner state, I think you'd run into all these problems of graphite you'd have to do something with your magnetic fields to create the potential minimum that it sat in to sit there and be observed. Mm-hmm.
Yeah. Otherwise it can just bounce off.
It would be very unstable to just flying off. The demos work because of vortices.
I guess you could stand a sumo wrestler on it or something.
On what?
So you could keep it in place using weight.
Yeah, but if the sumo vessel...
Right, no, that's right, it would flip sideways easily.
Yeah, I think it would be a brave...
Yeah, indeed. Yeah, actually, so that's an interesting point, that almost all of these levitation demonstrations are done in the vortex phase, right. And the vortex phase is doing useful work, basically, in stopping your superconductor from sliding sideways.
I have a question regarding the transition between the vortex and the Meissner regions. So we saw in the equations that basically for type 2, it's always convenient to have vortices. So what's actually happening there at a given temperature, so to say, even zero temperature? So why suddenly it's no more convenient to have vortices?
Yeah, why don't we admit vortices straight away? Yeah. I mean, I guess there's a very low field limit where you don't admit vortices because the total field would be less than half a flux quantum.
But even in that case, we saw that we should have certain flux, and therefore certain current.
Well, no, because so when we discussed zero flux in the cavity, we assumed the cavity had already been created. But now what we're asking is it worth to creating the vortex to admit the field? So the smallest vortex I can create admits a single flux quantum. If I have to run supercurrents to round up the internal field to that single flux quantum, that will at some point not be worth doing. So if the external field, if I admitted it through a vortex, would only give me half a flux quantum, or less than half a flux quantum, then it's not worth making the vortex to do it.
Yeah, but that doesn't tell you that isn't the answer to his question, and I can't answer it either. Yeah. But there's a
because that would be incredibly low.
That's right.
That would be like the rotation of a superfluid where you don't form a single vortex, which is very slow.
So there's a calculation that can be done that I could certainly not do, that considers the energetics of a single vortex formation in a type 2 superconductor. And it does give you this critical field for that single vortex entry. And then and that same calculation says that there's then an avalanche, right? So you're because I think this is not an answer properly to your question, but it's going to tell you a bit about what goes on. It's always useful to, I think, also to look at the MH curve, at least your calculation of the MH curve. So for a type 1 superconductor, it's just going to shoot up like this and then suddenly collapse at HC. Right? And we know that for a type 2 superconductor, what you do phenomenologically is you go up this curve for a little while, and then there's going to be some long tail where your magnetization is falling in the applied field because of the increasing entrance of vortices. But what actually happens is that there's a very sharp kink here because you hit whatever the calculation tells you for the critical field for the entry of one vortex, and as soon as one can get in, it just instantly becomes favorable to avalanche many more in. Mm-hmm. So the predicted equilibrium curve looks like that as a function of field. Might be useful actually for you to come and give us the single
work
vortex
out exactly what that thing
calculation
looks
next week.
Because there must be more to it than just saying less than half a flux.
No, there is more. There is more to it than that. It's done in detail in Walton's book, but I've completely forgotten it.
I think Derek Lee has that in his notes as well, so I'll have a look there. Just to check, I would have called this minus M.
Beg your pardon. Yeah, very good.
Right, remember this is diamagnetic, so
I PowerPoint all my lectures. I should never be allowed near a blackboard. And the other thing to say, which I've completely screwed up there, is that the area under the two curves has to be the same. If they were if you they give you what's called the thermodynamic critical field. If the things have the same heat capacity transition. Oops, many oopses.
Yeah.
Why did I do that?
I will check that and report back. You're right, there must be more than just the half flux quantum argument.
Probably within the order parameter itself, we should have some traces of these happening, actually. Before the order parameter somehow.
You mean after the vortices are introduced or before?
I mean, even in the transition, we have to see something happening.
I mean,
In the phase of the order parameter.
I mean, we have the same kind of thing to discuss here as we had in the case of the superfluid, because here we're just talking about static equilibrium configurations. But obviously there is a question of how we get there. So you can ask in the superfluid, well, how does the vortex actually get produced? And what tends to happen is it gets produced at the edge of the sample and works its way inwards. Something similar is often the case in superconducting samples. When you go into the vortex phase, there's defects and edges are more likely to be able to nucleate vortices because there the superfluid order parameter, the superconducting order parameter will be suppressed anyway. So it's easier to bring it down to zero and pop one of these things out. So there are nice videos, actually. The nice thing is these vortices are quite big. So if they move slowly, you can actually do microscopy on the surface and see them moving around. So there are real-time videos of vortices being nucleated and wandering towards the center of a superconducting channel and so on. And again, none of that's present in this theory, but if you're actually going to go through this transition, the dynamical aspects may be important, especially because depending on your parameters, vortices may be big, and so a kind of almost classical objects, right? I mean, they're living on a superconducting substrate, but they're large enough that they kind of move ponderously, and sometimes they jump. You see experiments where vortices jump from one pinning site to another and so on.
But even working time independently, we should be able to go from one point to the other one, and therefore we should find a limit between the two.
Yeah, I mean, I guess here we're relying on the thermodynamic limit to say that all we really have to talk about is the vortex density. So although we're discussing introducing a single vortex, actually that would make a strictly zero change to any of the energies if the system were infinitely large. So this line is where we go from a zero vortex density to a non-zero vortex density. If we actually drew this for a finite system, then there'd be a set of steps and things here, right, which would correspond to individual flux quanta being inserted, but we've taken the thermodynamic limit so that all of these curves become smooth. And so in that limit, I think you can only talk about the vortex density, and it will just grow from zero as you cross this line. But we will come back to think about the location of that line. We've a few minutes left. I think it would not be sensible to try and start the Josephson effect now. So the Josephson effect is the last of the Ginzburg-Landau type phenomena I want to discuss. So hopefully on Friday we can talk about that and then start thinking about microscopic questions like where did these charged bosons come from, what is their internal structure, and this kind of thing, and that will get us to Cooper pairing and sort of more modern expressions for this order parameter. But first, other questions on anything we've seen today? To remind you, basically, flux quantization, vortices, vortex phases, and the difference between type 1 and type 2 superconductors. Yeah, please.
So until now, you assume the size of the superconductor is large enough. When does it matter? Like when the energetics change, when the size of superconductor matters?
Yeah, so the most obvious answer to that question, which isn't always right but is a good start, is when the size of the superconductor is less than or of order of the coherence length.
But not the penetration depth.
But not the, so that will affect the field response, of course. But as a first, can I even talk about macroscopic superconductivity at all? That's really about the coherence length. And you can see why that is, right? If I have a broad superconducting sample and I plot the order parameter modulus as a function of position, it has to vanish at the walls. It recovers over a length scale given by the coherence length at either side. So you can see that if I make this sample sufficiently small, then, let me draw that again for a narrow sample. Then the Ginzburg-Landau prediction would be that it never recovers to the full equilibrium bulk value before it has to dive back down to meet the other side. Now, that's not to say that this isn't superconducting, but it's superconducting with a smaller order parameter, and therefore, well, probably then also a longer coherence length, so you have to do this self-consistently. But basically, finite size effects suppress superconductivity at the boundary, and because the boundary is now a fair chunk of the sample, they suppress it throughout the sample. Now, when you talk about fields, well, you can see that something similar will apply here, right? If I have a sample that's smaller than the London penetration depth, then if I apply a field on both sides, it will decay somewhat into the sample and then recover before it ever goes to zero. So what that's telling you is that the sample is now not large enough to run all of the supercurrents it would need to fully expel the field. There's just not enough space in the sample to carry those supercurrents. So it's all obviously about comparison of the sample dimensions with these length scales. Whether you should be comparing with the coherence length or the penetration depth depends a bit on the experiment you want to do. And obviously shape effects can become very important when the sample is small. If I have a disk-like sample, the response to a field along the axis of the disk could be quite different to a response to the field applied in the plane of the disk.
But then it seems like it's very hard to have any quasi 2D system to show any superconductivity, because the electromagnetic field still knows about the third direction. Mm-hmm. So is this the case, or is there some trick to have some superconductivity like thing in graphene and so on?
I think the answer is it depends what you mean by superconductivity. So there's no reason why you shouldn't have superconductivity in 2D with a well-developed resistive signature, for example. Because in transport, your charge can only flow through the plane that you're considering. So if there's a part of that which is doing non-dissipative transport, then you will see that in your transport measurement. But you always have to ask in lower dimensions, what do I even mean by bulk signatures? In the case of a disk, if I had a large disk-like sample and I apply the field vertically, that is to say out of the plane of the disk, then yeah, I guess the issue is There's another in principle, right? In principle, if you had a perfect Meissner effect in that disk, it would have to route all the field lines round it. But this is where we get into mixed state questions, right? It's going to become worthwhile at some point just to pay the cost of sending a chunk of the thing normal, not for vortex reasons, but I mean, now you can just take a little part of it and make it normal and say, I'm going to put the field through there. So, yeah, but I mean, but the standard bulk signatures are really based on being in 3D. And when the sample's 2D or quasi-2D, things are a bit different. I know in cuprates, for example, the vortices aren't really, even when you have a cuprate doing a vortex phase, the vortices don't really stick together from one layer to the next. And so you lose this idea of having a cylinder going through the whole sample. You have kind of 2D vortices that swim around. They have a slight tendency to stick to each other, but actually it's not that great, and you can get into phases where they're wandering independently.
But that sort of argues against the point you were speculating about, that you simply can't have 2D superconductivity. I think these layered compounds are quite informative there, because as you make them layered, right, and you pull the layers apart, you've got to be aware that the coherence length is very anisotropic. Right, so I think you were worrying about the depth dependence relative to the coherence length, but the coherence length shrinks in the C direction as you reduce the coupling. Right? And so you can perfectly well have, if you could take a snapshot of a layer in this cuprate where the layers are basically decoupled, as Chris says, you still see vortices in all the standard magnetic responses. I think that was because the C-axis coherence length has become so small. And they've decoupled because the C-axis coherence length is so small that they really aren't three-dimensionally coherent superconductors anymore.
Yeah, there's an extra comment I could make about that, but it relies on the Josephson effect. So let's wait until we've talked about the Josephson effect.
Yeah.
Okay, great. That's 12 o'clock, so let's leave it there for now. Thank you everyone as ever for your questions, and I'll see you on Friday. In hand.